In this lesson, we will look at secondary cells, which are the type found in aircraft main batteries. We will look at how these cells can be joined together to form batteries with different voltages and current supplying capabilities. Secondary cells work on the same principle as primary cells. They have two electrodes immersed in an electrolyte. The chemical reaction between the electrodes and the electrolyte causes a potential difference to build up between the two electrodes. When the positive and negative terminals of the electrodes are connected to an external circuit, electrons flow from the negative terminal to the positive terminal through the circuit. At the same time, more electrons are allowed to transfer inside the cell from the positive to the negative electrode. As this circulation of electrons continues, the chemical makeup of the electrodes and the electrolyte changes. When all of the chemical energy is used up, the potential difference will fall to zero. The difference between a primary cell and a secondary cell is that in a secondary cell, the process can be reversed. The chemical energy in the cell can be restored, and the changes in the composition of the electrodes can be reversed by passing a charging current through the cell in the reverse direction to that of the discharge current. This current is forced through the cell by applying a potential slightly greater than the cell potential to the cell in order to reverse the flow of electrons in the cell. In this way, the secondary cell can be discharged and recharged many times. The capacity of a cell is a measure of how much current it can provide for a specific period of time. Capacity is measured in ampere hours, or Ah, and is determined by the surface area of the electrodes, or plates as they are often called. The larger the area of the plates, the greater is a cell's capacity. There may be a number of plates joined together in parallel in each cell to increase the capacity of the battery. The groups of positive and negative plates are slotted together to form a cell. A cell with a capacity of 80 ampere hours, for instance, should theoretically provide a current of 8 amps for 10 hours, or 80 amps for 1 hour. In practice, the capacity will reduce as the rate of discharge is increased. A cell's rated capacity is normally measured at the 1 hour rate. We will now look at how cells can be connected together to form batteries of different voltages and capacities. On the screen is the symbol used in electrical circuits to depict a cell. The long line is the positive terminal and the short line the negative. A single-cell battery may be used on its own, or cells may be connected in series or in parallel, depending on the voltage and capacity required. For cells connected in series, the positive terminal of one cell is connected to the negative terminal of the next, and so on. The total voltage is the sum of the individual cell voltages. So, for instance, if 3 2-volt cells, each with a capacity of 10 ampere hours, are joined in series, they will produce a voltage of 6 volts. But the capacity will be the same as for a single cell, in this case 10 ampere hours. If the same 3 cells are connected in parallel, that is to say, the positive terminals are joined together and the negative terminals are joined together, then the total voltage will be that of one cell 2 volts. But the capacity will be the sum of the individual cell capacities. In this case, 30 ampere hours. The cells can also be connected in a combination of both series and parallel, allowing both the voltage and the ampere hour capacity to be increased. As an example of this, if we take 4 2-volt cells, each with a 10 ampere hour capacity, and connect them as shown, you can see that we have 2 pairs of cells in series, with the pairs being joined together in parallel. We add the series voltages together to get the output voltage, in this case 4 volts. And we add together the parallel capacities to ascertain the total capacity, in this case 20 ampere hours. As we have previously said, a battery consists of a number of cells connected together. If 2 or more batteries are connected together, then the same rules apply as for the joining of cells. So if 2 12-volt 80 ampere hour batteries are connected in series, they will act as a single 24-volt 80 ampere hour battery. But if they are connected in parallel, they will act as a single 12-volt 160 ampere hour battery. That is the end of the lesson. You have learned the following key points. A secondary cell can be discharged and recharged many times. The capacity of a cell is a measure of how much current it can provide for a specific period of time. It is measured in ampere hours. If cells or batteries are connected in series, the total voltage is the sum of the individual cell or battery voltages, but the capacity is that of a single cell or battery. If cells or batteries are connected in parallel, the voltage is that of one cell or battery, but the capacity is the sum of the individual cell or battery capacities.